And here we go. All right, welcome back. We are Game 3001 in the summer 2022 semester at George Brown, and it's week 9. And this is our lecture recording for week 9 in the summertime for artificial intelligence. This week we are talking about decision making in general and also decision trees. And I'm your host for this week again in the second half of semester. That's me. If you haven't met me before, or if you're new to the class, hopefully you're not, because that would be really weird. So again, we talked about this briefly on Tuesday when we got together in person, that this week is all about an intro to decision making and decision trees. We're also going to revisit the tree data structure starting this week. And the reason for this is because some people may not know what the tree data structure is. They might know C++, but they've never done any kind of data structures course. And I think that that is something we need to talk about, how to build a tree and all those kind of things. So the second half of the semester is largely going to be involved with decision making. So the first half, you guys did pathfinding, and you also did steering behaviors, which I think they're awesome. Combining pathfinding with steering behaviors and then adding in decision making, you can make a much more believable AI. And the more believable your AI is, the better gameplay is. A lot of times more challenge for the players and those kind of things. So that's what we're doing here in the second half. So as you notice, here's the schedule. So this week we're talking about decision making and decision trees. Next week we're talking about state machines. We're following that up with behavior trees on week 11. And that is when assignment 3 is due. And we'll talk about assignment 3, 4, and 5 today in more detail. I talked about it briefly during our in-person lab on Tuesday, and I'll talk about it again today and to make sure that you have everything that you need. After that, we're going to be going with goal-oriented behavior in week 12, utility theory in week 13. I was going to say grade 13. I don't know why I thought that. And then finally, tactical and strategic AI. And the very last week is going to be, more of more AI related to things like reinforcement learning and as well as machine learning, which how machine learning kind of works with this the last week, machine learning, reinforcement learning, Q learning, and all those kind of things, and how they're going to wrap into game development. Not something that is as common, definitely, as decision making, but we'll be talking about that during the last week. Again, in terms of your evaluations, we're sitting at, again, week 9. So the focus is going to be on getting you to finish assignment 3, which is a group assignment. Okay, it's due week 11. That's the Sunday of week 11. And it's worth 10% of your final grade. And so we'll talk about that coming up in a bit. Last time we were together, you talked about, or you were together with Alex, you talked about A-star pathfinding mostly, and pathfinding in general. You finished off lab 5. And we talked about some feedback for assignment 2. Some of it was good, some of it wasn't so good. And Alex put out an interesting note this week about some of the stuff that was published for assignment 2. So hopefully you got that. But this week we're going to be talking about decision making and decision trees. We have lab 6 started in the in-person part, and it's going to be due, the final version is going to be due next Sunday. I believe that's July 17th, if I'm not wrong. Let's take a look. So this Sunday is July 10th. Next Sunday is July 17th. It'll be July 17th, due July 17th at midnight. Again, it's worth 8% of your final grade. Please don't take it lightly. These things are considerable in terms of how they may impact your your final mark, right? So please take them seriously. Stuff that's been released that's up online, assignment 3, 4, and 5, and I talked about with you on Tuesday very briefly that you need to sign up for groups of up to 3 members in A345 group set. Let's go there first. And I'm going to talk about the assignment first before we get into the lecture piece, just to make sure that you have that out of the way and that you don't have to think about it after, right? So if we go into users and groups, if you look at groups, You can see that there are several for assignment 1, and I know Alex created some of these as well. But if you kind of scroll down or click through to the next group set, you can see that there is a A345 group set, 1 through, I think it's 40. So please sign up today. Don't wait, because if you don't sign up for a group set, you will not be able to view or submit your assignment 3, 4, or 5. So why have we done this? Why A345 as opposed to how we did it before with A1 and A2? A1 and A2 were kind of separate, and they had kind of no relation to each other, not really. But A345, they're all kind of related, and I want to talk about all those assignments in step today. Let's start off with assignment 3. So let's go through these details a bit. So if we look at assignment 3, and assignment 3, the outline is up online as well for you guys to look at. But I want to talk about this in a little bit more detail today than we talked about on Tuesday. Since Tuesday, we kind of were more focused on lab work than anything else. So this is, again, due week 11. So it's Sunday, July 24th by midnight. The assignment is kind of your foundation for decision making, which we'll talk about today. For this assignment, you may work alone or with up to 2 partners for a total group size of 3 members. Okay, now I talked about this on Tuesday, and I'll repeat myself today. I don't recommend working alone on this one. I think that working alone would be a bad thing. And the reason for this is because there's a lot of work involved in getting this assignment going. This assignment, actually assignment 3, 4, and 5, which are related, as an example, were created by myself and Alex. So, and it was made for kind of the original way we did this course. The first iteration was there was a project for the entire course that you'd kind of work on. And we kind of removed that, and we made individual assignments to make it easier for you to digest some of the content, because there's a lot of stuff to know when it comes to AI. So some mandatory criteria are going to be kind of indicated, just like you saw in the previous 2 assignments. Here's your project setup. You're going to have a start scene, 5 points. This is kind of a freebie. If anything else, if you use the framework, which is what we recommend to you to use, then you'll be able to get a start scene. And what you need to do is put all the names of the people that are involved in the project in that start scene. So even though the default scene right now goes right to the play scene for us when we're working in lab, please make sure that your default scene starts at the start scene for your assignment, and that we can see your student IDs and all those kind of things. You're going to, if there's not a button, and there is a button already there, it's the start button that's going to take you to the play scene. This, again, is 5 free marks for you guys, as long as you add in this stuff, the information about you and your partners. Okay, that's in here. For the play scene itself, the play scene will demonstrate decision making. That's the main thing. You must include a node class. Okay, this is interesting. A node class that we haven't done yet. We're going to work on this. And you must create a collection of node pointers to enable iteration across all nodes. And again, this could be an STL vector, a list, or other structure. And ensure you select an appropriate actor sprite. So the node class that we're kind of working on now in Lab 6 is path nodes. That's what we're making. So that's kind of exactly what we're asking you to do, path nodes. So an appropriate actor sprite, whenever we say this kind of stuff, right, what we're trying to tell you is that we need you to select your own textures, okay? So your own sprites, the stuff that we share with you in lab. So that's, for example, lab 6, the current one we're working on right now, has a little ship and all that kind of stuff. But for you have to get your own textures, you have to get your own backgrounds and all those kind of things. That is part of the work that you need to do for your assignment 3, 4, and 5. Please do not use the stuff that we've given you. That is demo stuff. That is placeholder stuff. You have to make use of your own, kind of assets for this thing. So again, this could be a spaceship, a car, animated character, other appropriate vehicle or avatar. Most likely a good choice for this might be some kind of vehicle or avatar that can both do combat, like close combat, as well as ranged combat. And the reason why I'm saying this is because I know what assignment 3, 4, and 5 is all around, right? So the actor will be able to move in any direction by responding to key presses. You'll be able to move it with WASD keys or by using the left stick on the gamepad and face in the direction of the mouse pointer, or by using the right stick on the gamepad when you're moving. Okay, so you make it kind of like a twin stick shooter if you want to, or twin stick controls, or you can use just keyboard controls, which might be easier. Create an interesting map. Okay, so whenever we say interesting map, again, we get an array of stuff back to us. I'm talking about myself and Alex. An interesting map for me means you need to kind of grab either a good background. You could use a tile set. Alex in the previous labs has given you a tiled map that you can implement again. Even though I'm giving you stuff that doesn't include a tiled map right now, it's not like you couldn't include them or incorporate your tiled map inside of your assignment 3, 4, 5. So the thing about this is that the interesting map should be overlaid on top of the nodes. So again, instead of tiles, your interesting map's not overlaid on top of tiles. It's overlaid on top of nodes this time around. Okay. And you can make this a bit creative. Ensure the map includes obstacles, mountains, walls, debris, whatever, that are impassable. So things that you can't get through. And you may use a tile map set or simply draw your map as tiles individually. Your play scene must include appropriate background music. So this is all set up. And there should be sound effects for all actions or triggers in the play scene. Any clicks, any kind of motion or anything like that should have sound effects. Requirements. This assignment will set up all the key elements that will be reused in assignment 4. So again, 3 is your foundation, 4 is kind of the final version. If you think about this, this is like 2 different releases, almost like a first playable release, which is for your assignment 3, and your final release, which is assignment 4. Okay, so 2 little releases for a little project for AI. A lot of this will also help you with game production too. So if you're if you're creating more of an advanced AI for game production too, this will help you out to do that kind of stuff, because the stuff we're talking about here will be applicable there. In your debug view, we say when the user presses the H key, your program will toggle the debug view on and off. Again, we also have the backtick character that will also bring up IMGUI. IMGUI is in the place of your debug view. When we say keys here, I say you need to press the H key or the P key or something like that, or the K key. A lot of this can be done instead of debugging keys. I will accept IMGUI kind of controls and making use of buttons and stuff instead of just using debug keys that are listed here. But let's talk about what you need to do on IMGUI instead. If you can use keys like we said here, or IMGUI is okay. When the user presses the H key, your program will toggle into debug view, which will display line of sight rays. Okay, so right now the line of sight ray is visible in lab 6 because we made it visible. But reality is you shouldn't see the line of sight ray in gameplay. It should only be seen as a debug version of what you're doing. There's 2 things we're looking for: line of sight as well as something called detection radius. These 2 things, in addition to other things, are part of your AI's sensing suite, okay? Sensing suite, which includes both those 2 capabilities. A detection radius, there's a bunch of ways to do this. One way is to detect the distance. The other way is to overlap a circle. So there's 2 different ways of doing this. Collider boundaries. Collider boundaries are the collision areas, right? Or collision bounds for your objects, okay? So collision boundaries. And node points. Node points would be, again, your path nodes that we did in lab 6, started in lab 6 on Tuesday. So that is your debug view. Debug keys, or buttons, in this case, if you're using IMGUI, the K key or some other button, when the K key is pressed, the base enemy class, which is what you're going to be making, will take damage. So the enemy will take damage automatically by pressing a key. This will be a simulation to kind of see what happens when the enemy takes damage, okay? When the P key is pressed, or another button in IMGUI, then the base enemy's movement will be toggled between idle and patrol, okay? So then it'll actually turn patrol on, okay? Or turn patrol off. So that's one of the things you're going to do. So you're going to have the base enemy kind of walk around or move around the screen in some kind of patrol pattern. Okay, that's what we're going to be doing. Player animations and sound effects. The user will trigger various animations and sound effects for the player: an idle animation when no input is triggered, a movement animation and related sound effect when key presses, WASD, is made, or gamepad input is triggered, a close combat animation and related sound effect when the left mouse button is pressed or the lower face button on the gamepad, and a projectile firing animation and related sound effects when the right mouse button is pressed and the right face button on the gamepad is pressed. So again, a lot of this stuff, the player animations and sound effects stuff, is all set up and has nothing to do with AI. You can start this today, okay? And that's why I recommend getting moving on this with you and your partner. So you don't need all the stuff that you're don't wait, in other words, for lab 6, lab 7 to be to be started and all the stuff I'm going to give you. Start with this now. You can always reintegrate this stuff later on so that you're ready to go with your assignment 3, which is due in only 2 short weeks from now. Okay, so get this started with these animations. Again, you can download animations from Open Game Art. You can certainly create your own, but I don't expect that at all. Player combat capabilities. So the player itself, not the target, but the player, the player that you're controlling, can engage in both close combat, melee, okay, and range combat, shooting. Okay, you can do both things. For close combat, the player must be within an appropriate range. You determine that. What is an appropriate range? It's up to you. And be facing the enemy in order to register a hit. For range combat, the player will fire an appropriate fire and forget type projectile, which Alex has talked about in your fundamentals courses, in the direction they are facing, and the player's orientation is set to follow the position of the mouse pointer or moving the right stick on the gamepad. One of the 2 ways of doing that, okay? So that's your player combat capabilities. They will be able to fire a bullet, okay, at the end of assignment 3. You're also going to have a player health bar. Your player must include a health bar object that displays the health status of the player in real time. So again, a health bar, lots of ways of doing that. I think that was also covered for the most part in your fundamentals courses, for how to do that. What is a health bar? It's like a progress bar, and there's many ways to create that. This could be a solid bar or a series of symbols. I recommend a solid bar. It's a little easier to do than a series of symbols, but if it's easier for you to do this part, it's okay too. That's why we put either one or the other. So that is your player health bar. Game status. Your play scene will include a progression bar, another progress bar, score label, or other type of control that will display how many enemies are still active in the scene and how many have been eliminated. All right, so in other words, you'll be able to eliminate enemies in the scene. You'll also have obstacles. Your play scene will include at least 4 obstacles that will stop the player and the enemies from passing through them. So notice that it's also the enemies that will be stopped, not just the player objects itself. So you won't be able to pass through obstacles or under them or over them or anything like that. These obstacles must be solid and impassable, and these obstacles will also block enemy line of sight. So if the enemy trying to detect the player and all that stuff. However, they will not block enemy detection radius, because that's the other way, the other part of sensing for your enemies. Okay. You are going to set up something called a base enemy. Okay, the base enemy class is something you're going to extend and improve upon in assignment 4. So that's why this is a fundamental assignment, almost like a base assignment for assignment 4. Your game will include a base enemy class. The base enemy object will move or patrol along a predetermined path of nodes. So again, remember we set up these path nodes for you guys in this week's lab session. You can use those path nodes as position points, right? So you can load them into a path, and you can have your enemy kind of follow along the path, do a path following, if you will, around the map. Okay, the base enemy game object will have a health property. So again, think about the health property will be displayed in a health bar. So we talked about earlier how your player will have a health bar, right? There's your player health bar. And you're also going to have a health bar for your enemy. Again, this could be a way, if you wanted to make a health bar class, something that you can add to both the player and the enemy, something you can reuse. You don't want to make a brand new object or brand new class for each thing. So your enemy and your player could use a composition instead of inheritance to include a health bar object inside of it. Okay. When the enemy game object is hit, the health bar will display the correct value. Okay, so that way you want to see what the value is of the enemy's health, and that's something that the base enemy will start off with. Okay. Base enemies will also have animations and sound effects. again, if you read through this, they're going to have several states: an idle state, a movement state, a damage animation, and a death animation. Again, guys, and everyone else here as well. One thing to note is this is not dependent, again, on any AI patterns or algorithms that I give you over the next little while, which means for both player and enemies, get those animations going, right? So if you're working with partners, which I recommend, then have your partner or you, kind of divide the labor and get those animations going and implemented in the game. So that way you're ready to go with this stuff instead of waiting to the last minute, okay? So you can have this all working. These are worth points for you to do this. You're getting paid to get these animations going. So please go and do that stuff. Your base enemy line of sight is the stuff that we've been working on, starting to work on with Lab 6.1 anyway. Each base enemy will need to calculate and keep track of whether or not they have line of sight with the player. So do they have line of sight or not? You will need to account for any obstacles that may block line of sight in this calculation, and the result can be stored in a Boolean. We've already kind of did that, has line of sight, in an instance property on the enemy. All right, so this is something that you can keep track of for each of the enemies. Enemies will also have something called a detection radius, okay, and we set up a simple algorithm that determines if the player is within each enemy's detection radius, which can be the range of your choosing. Like the line of sight check, it can be stored as a Boolean and will be used for the next assignment. So why do we need, what is detection radius? Think about this as you can hear the player. The enemy can hear the player, or maybe they can smell the player or somehow otherwise detect them, okay? So even if the enemy can't see the player's not in their line of sight or too far away, maybe the detection radius will say, okay, I detect the player. I can detect the player. I know the player's around, right? But I don't know where the player is, okay? Not exactly. You definitely have to use Git and GitHub for source control, and there are some submission criteria for kind of submitting to Blackboard. You also need to make a short video presentation as normal for you. Again, the recommendation is that you and your partners all talk about what you're doing for this particular assignment. But you could also just have one person go through the video itself and do the presentation. Okay, so that's something that can happen as well. Short video should run no more than 5 minutes. You can show mostly everything. I don't want to see your code necessarily. I just want to see the behavior of the enemy and the player. So show me that you can move your player around. Show me that the enemy has a detection radius. Show me the debug view. Show me all those things. That's what I'm looking for. I don't want you to, to read your code. Okay, so penalties are like normal, like we've talked about before, and the breakdown of your rubric is here. Okay, so this is where all the marks are going to come from. And this is out of 100%. Okay, so this is, or 100% for this particular assignment. Okay, so this is assignment 3. Questions around assignment 3 or concerns around assignment 3 and the time frame. Again, if you look at the time frame right now, you're given until Sunday, July 24th. It's not a lot of time to get this going. Any questions at all? Again, if you're just joining, welcome. We're just talking about assignment 3. And we're going to be talking about assignment 4 in a second. Right. So Derek says, what is game style or format should be? Let's wait up, Derek, and I'll show you. You can decide what game style. I mean, like, are you talking about theme that you want? Or do you mean controls? So controls are WASD. It's a top-down style kind of game. You're not doing... you're definitely not going to do some kind of scrolling game or side-scrolling or anything like that. It's a top-down type of environment we're talking about. Okay, so that's what it's going to be. All right, so that is assignment 3. Let's look at assignment 4 now and how it plays on assignment 3, how it kind of builds on assignment 3. So assignment 3, again, is due 2 weeks from now. Assignment 4, let's take a look at assignment 4. Again, this is all up on Blackboard for you as well. So you can take a look at that. Assignment 4 is due week 14. So that's a little bit more time and you need it. Okay, so again, between week 11 when assignment 3 is due and week 14 when assignment 4 is due, you have 3 weeks to do this stuff. Guys, please don't leave it to the last minute. This is heavy duty in terms of the stuff that's due. Okay, for this assignment, you may work alone or with 1 or 2 partners for a total group size of 3 like normal. the recommendation is you stay with the same group for the summer, right? So that's why I've made a group that is called, or group set that is 8, 2, 3, 4, 5 groups, because this way you'll have a chance to stay with the same groups, and you're going to build on what you did for assignment 3. So again, this is due Sunday, August 14th. Sounds like a long way away. Guys, for what I'm asking you to do, it's not a long way away. It's around the corner, truly, right? So mandatory criteria are the same. Now here's one that's mandatory. You must have assignment 3 completed for assignment 4 to be kicked off. Think about your assignment 3 as a starter for assignment 4. And by the way, I want separate repositories. I don't want assignment 3 and assignment 4 the same repository. Create a new repository for assignment 4. All right. So you're going to use assignment 3 as a starter, and then you're going to build on assignment 3 for assignment 4. Okay. So now what we're going to be talking about is you're going to build something called AI actions. So here are the actions that your enemies will now have in assignment 4. You will be able to patrol from assignment 3. The enemy will patrol along a predetermined path of nodes around the map. You will play and move the move animation and related sound effects while they're moving in patrol mode. They will have a move to player action, which requires line of sight. They will move toward the player using the arrival steering behavior. So notice how we're including arrival as one of the steering behaviors from assignment 1. All right, this is something we talked about. And they'll stop at close combat distance. Now that is something that you need to determine what close combat distance is. Should be a certain number of pixels. That will make sense for your avatar, your player, and the enemies, whatever you decide to choose. You'll play the move animation and related sound effects. Okay, so that is move to player. Close combat attack requires line of sight and close combat distance. You'll play the close combat attack animation and related sound effects and start damaging the player. So that is an action that you can take. Flee. Move away from the player, avoiding obstacles and leave the scene. Play the move animation and related sound effects. Move to line of sight. Move to line of sight. So if you don't have line of sight, then the enemy will have to move to line of sight. Find the closest node to the player with line of sight. So each node then, which we talked about last time, will kind of keep track of line of sight with the player and with the enemy. And this is really key, because if the nodes are intelligent, the path nodes, then they'll be able to inform the player and inform the enemy specifically, more specifically for the AI, if they have line of sight or not. Use obstacle avoidance along the way and use the seek steering behavior to move. So again, look how we're incorporating assignment 1, obstacle avoidance, as well as seek steering behavior. You're going to play the move animation and related sound effects. Okay. Move to range, another action. So move to line of sight means I don't have line of sight, I'm moving to line of sight. Move to range requires line of sight. So move to range. Range is usually for range combat. Use a blend of separation and cohesion steering behaviors to maintain an appropriate distance from the player. Play the move animation and related sound effects. Okay, so that's what you're going to do to move to range. Move behind cover. This is another action. Find the closest node to the player that does not have line of sight and move there. Right? And play the move animation and related sound effects. Wait behind cover. The enemy must be behind cover. The enemy will wait for a random interval and then leave cover. So you're going to move behind cover, the enemy, and then wait behind cover for some random interval, right? And finally, the ranged attack action. The ranged attack action requires line of sight and the enemy at the appropriate range. Those two conditions must be met. Play the ranged attack animation. Generate a projectile that moves towards the last position of the player. So don't keep tracking the player. There's no tracking necessary. If the projectile hits the player, then apply damage to the player. Okay, so those are all the actions in no particular order that your enemy AI will have to have access to. So how do you implement these actions? We're going to ask you to create 2 enemies or 2 loadouts. The first loadout is a close combat enemy. Okay, so again, think about how we're going to use the base enemy class from assignment 3 to extend that so that you can create something called a close combat enemy. Starts in patrol action. That's the way it's going to be, and continues this action until they have detected the player somehow, either by line of sight or the player is within their detection radius. Those are the two ways they can be detected, the player. If the player is in their detection radius and they do not have line of sight on the player, perform the move to line of sight action. So if I can't see the player, as an example, but if the player is in the detection radius, so if the player's been detected, right, then move to line of sight. Try to go to the nearest node that has line of sight with the player. The nodes will tell the enemy if they have line of sight with the player or not. We'll be talking about that in the next series of labs. If the close combat enemy has line of sight, so we can see the player, perform move to player action, because this is a close combat enemy. So we're going to move closer to the player. If the close combat enemy has line of sight and is within close combat distance, so close enough, perform the close combat attack action. So attack the player, right? If the close combat enemy's health drops below 25%, they will perform the flee action, right? So notice how the actions are going to be used for each of the loadouts a little bit differently. So this is your close combat enemy, an enemy that'll come in and try and do a melee attack on the player. The other loadout is the ranged combat enemy. Create a subclass of the base enemy class from assignment 3. Notice how we're again depending on this. The ranged combat enemy will include the following behaviors. Starts and patrol action like normal. If the player is in their detection radius and they do not have line of sight on the player, perform to move to line of sight action, which is very similar to what we did here. Notice that these two parts are exactly the same. However, the next parts are a little different. If the ranged combat enemy has line of sight, perform a move to range action. So they're not going to come into range of the player like close combat range. They're going to stay away, right? To keep a nice ranged combat, distance away from the player. If the ranged combat enemy has line of sight and is at an appropriate range, you determine that, right? Perform the ranged attack action, with trying to attack the player. They're going to actually fire a bullet or some other kind of projectile. If the ranged combat enemy is hit, perform the move behind cover action. So the first time they get hit, and this is different than, this is an extra piece compared to the close combat enemy, right? If they get hit, they're going to move behind cover. So they need to detect where the nearest node is that has no line of sight with the player, and then move there. And then they're going to wait behind cover for a random interval. And then finally, if the ranged combat enemy's health drops below 25%, they will perform the flee action. So this is the guts of the assignment 4. Assignment 4 basically allows you to create an enemy, 2 different loadouts based on assignment 3, right? So you're going to build on the stuff that you've made in assignment 3. It's not something that you're going to be asked to do in 2 weeks. It's going to take a few weeks, 4 or 5 weeks to do properly. But at the end, you're going to have a really nice enemy that you're going to, AI that you're going to be able to kind of show off for your assignment. Other things to make this a real little game, right? One is a destructible environment. So create a subclass of the obstacle class from assignment 3 and name it destructible obstacle. This class will include a health bar of its own, and you'll be able to destroy the obstacle, make half of the objects in the scene destructible. So if before we asked you to make 4 obstacles, now you might have more, but half of them should be destructible. Enemy respawning. If an enemy flees the scene successfully, then a new enemy will respawn, enter the scene within a random interval. The new enemy can be of either type or loadout, and this should be determined randomly. So if a melee or close combat enemy flees, a remote or ranged enemy could come back. Okay, it's really random how this should work. For the win condition for this little project that you're making, if the player defeats both enemies without either of them fleeing, so if you're able to kill them both before they leave the scene, then you win the game. Display a label object that reads "you win" or something similar, and display a restart button that allows the game to restart. Again, use Git and GitHub. Make sure that the GitHub repository is different than assignment 3, so it's a separate repository. And again, same submission criteria, assignment 4, and so on for your short video presentation that you're going to make. And all the rest of the stuff is pretty much the same, but this assignment is weighed at 15% of the final course grade. Okay, so it's a little bit heftier than the first one. These 2 assignments put together, assignment 3 and assignment 4, are worth, think about this for a second, right? 25% of your final grade, just those 2. All right, and there's the rubric for what I'm looking for for all the stuff for assignment 4. Any questions around assignment 4? Again, it's hard to see this because I'm kind of going over these assignments now with you, and the reason why I'm doing this is so to give you an idea of what we're building in our labs, Lab 6, Lab 7, Lab 8, and so on, okay? And you may think about other questions later. Okay, nice, excellent. All right, but let me give you an example of a student's work that they made for this. This is an alumnus, right? So this is something that a student created. So I'm going to show this with you, and you can see what they made for AI for us. I'm going to share Sam with you as well, and hopefully you'll be able to see this. I'm also going to optimize for video clip right now so you can see how this looks. Okay, so this is their assignment 3, or 3 and 4, okay? So again, you have control over your player, okay? You have different kinds of enemies. I can attack, right? I can also fire a button, right? So I can fire those kind of things, right? You can see that different kinds of enemy. He also made, in this case, an enemy that has both types of loadouts. So you see how they run away, right? So you can see that the environment is destructible. And if I just defeat this enemy, which I was not successful, then I can live. Otherwise, I'm going to not do well. Oh, here's the knight. The knight has armor, and you can see how I died. Okay, there you go. So that is an example of the final version of assignment 3 and 4. Okay, that's Herman's version. It was, again, an alumnus that was here at George Brown that used the exact same criteria that you're having right now to create their game. Okay, now, do I need you to do this? This is an A+ kind of effort on his part. He worked alone to do this, so he didn't have a partner or anything else like that. Again, very innovative student, used a tile map, again, some different actions, and all the stuff that we asked you to do here is being covered. Notice that if I press the debug key that we allow, we can see things like your colliders, the nodes that he used, which he kind of used sparse nodes for things like movement, as well as for line of sight and so on. And that's what he kind of put together. He even put together a trap area and a bunch of other stuff to make the game more interesting. So if you try again, you can see that we can see it in what it looks like in debug mode. You can see that. And you can see that the player is going to have both melee as well as range combat capabilities, right? All right, so that's kind of it. It's kind of a tough game, to be honest, but interesting, right? And you can see that as long as I don't let those creatures go away, I might be able to complete the game. Let's see if I can do that. He's going to go through that. Oh, see, no, it's not going to happen. I'm just not fast enough. Okay, that's kind of the gist of it. Questions around assignment 3 and 4. So this is kind of an example of what can be created for assignment 3 and 4. It's not, if you can't make it so as complex or nice, it's okay as long as you meet the criteria. Notice that, again, he's not using any of the assets that we're showing in lab. That's not required here. It's truly just for, he's made his own assets, or used his own assets from the open game art or some other place. One last thing, assignment 5. So what is assignment 5? Well, actually, I think it's probably the easiest of the three. Assignment 5 is actually just the final presentation. So there is no final exam in this course. Assignment 5 takes the place of the final exam for this one. Now, this is not due on the last Sunday. It's due on the last Friday of the semester. So again, if you look at the semester, and if we look at August, we can see that the last Friday happens to be August 19th. That is when this thing is due. So again, your team will present the final version of your decision-making assignment A3 and A4 for this semester. You must be prepared to present live. Use a slide deck during your presentation to keep you organized. Your presentation should be no longer than 5 to 10 minutes. You'll be marked on the quality of your presentation materials, your presentation style, and the quality of your game demo. All right, so that's what you're going to be doing. Again, we can talk about this again, but for the most part, you're going to have a small slide deck, right, or PowerPoint slide deck that you're going to use to organize yourself. We'll talk about more of this when we come closer. You're also going to be marked on your presentation recording and your gameplay video. as well as your live presentation that you're going to be asked to do during class. Okay, so that's what I'm going to be asking for. In the last week of class, you should be ready to present. All right, so that is your final presentation. That's assignment 5. So really, assignment 3, 4, and 5 is all about decision making. And if you think about that, that is the second half of semester, and it's worth 31% of your final grade, not including anything to do with labs. So kind of a hefty piece of work. That's why I recommend combining with at least one other person to get this done. I think it'll lighten the load for you guys and get this done. And then at the end, from a course outcome perspective, it's going to cover everything you need to make a pretty slick AI in any game system and any game framework that you use from here and throughout your careers. Okay. Questions around assignment 3, 4, and 5. How about I say concerns about assignment 3, 4, and 5? What about that one? And you can come on the mic, guys, even though you're being recorded on YouTube. Who cares? Come on and talk about it. I'd rather hear from you than not hear from you. And maybe you're going to have questions about this later, but I wanted to talk about this first before we move on. Okay. Hopefully you guys are alive out there. But, you know, I just wanted to make sure that you understand what's due. All right, so that's assignment 3, 4, and 5. If you do have questions, I'll definitely answer them. And that's why I say please sign up for groups of up to 3 members today. Don't wait to do this, and don't wait to start your animations and all the sound effects and everything else you need to do. You can get going on that and make little experimental scenes that have nothing to do with the AI stuff, just to make your player and your enemies work properly. And then once you have that, you can also just incorporate those things inside of your assignment 3 and 4. Okay, let's talk about the next piece that I want to talk about now, which is decision making. This is a new topic we're going to work on from this point on. And this topic is something that's going to help you with your assignment 3 and assignment 4. So again, when we think about decision making, what is that? Which is really the ability of an autonomous character or an AI you know, to decide what to do. Before, what we've been working with up till now is, you know, the ability for us to steer around a game. Okay, that's what it can do. We've also been working on things like pathfinding. Okay, but we can sometimes see pathfinding as almost unfair for the AI. Think about this as an example. Unless you're playing a turn-based strategy game like XCOM, right, as an example, right, then having a real pathfinding algorithm for an AI to go from one place to the other, it's like they inherently know where the player is, and somehow that can be unfair in a game. So we want to do something different in this second half. We want to talk about the ability for the AI to detect the player, almost like act as if they are a non-player character or enemy, a challenge for the player. That's very different than using pathfinding or just simple steering behaviors. Okay, so it's not about that. This becomes where we were trying to make it so that the AI is more realistic. Most games, when we talk about this, they use simple decision-making systems like decision trees, state machines, and behavior trees. Okay, those are the 3 types that are being used. You know, when we talk to the people at Ubisoft, and we have our annual meetings with Ubisoft faculty night, they talk about what they're looking for to hire a student. And the main thing they always talk about is students should know, you know, kind of your you know, data structures. They should know about collections. They should know about, you know, basics to get them going, to hit the ground running. And one of the things that you know about AI is decision making, how to do decision making, steering behaviors. All the things that we're teaching you about in AI this semester are all the things that are going to be required for you if you're thinking about going to become an AI programmer or something like that in the future, or even if you want to make your own game that's kind of pretty cool and challenging for the player. So decision trees, state machines, and behavior trees are common. They're very simple, and rule-based systems, that's something else, are rarer, but they're also cool to have in the game as well. When it comes to our AI model that we've been looking at this semester, right, then decision making is kind of in the middle of our model, okay? And we're going to be talking about both tactical and strategic AI in the second half of semester as we go forward. So really what we have is the character processes some kind of set of information that it uses to generate an action. And this set of information is going to be based on what it can see, what it can detect, as an example. And then this input to the decision-making system is the knowledge that an autonomous character possesses, and the output is an action request. So remember we talked about all those actions in assignment 4. I said you need to have all these actions. How do I make all those actions happen? Well, if you think about it, the actions for assignment 3 and assignment 4 are going to be based on the input that the AI is getting from the environment. Okay. So one thing that I wanted to show you really quickly is kind of like a little layout for what assignment 3 and assignment 4 could look like. So think about these are little path nodes as an example, right? And then there are really 4 cases when it comes to assignment 3 and assignment 4, for the enemy and the player. Okay, so here's case number 1. So line of sight is false and radius is false. So why? If this is the player, you can see that the base enemy can't see through the obstacle, right? So there's no line of sight, because we talked about line of sight is if I can cast a ray, a line segment that goes from the base enemy or the enemy class to the player class with nothing in between, okay? So you can see that this obstacle is actually closer to the base enemy than the player. Therefore, we can say that the base enemy does not have line of sight. And the radius, this detection radius, which could be a circle or it could be a range, for example, some kind of just a number, distance from the player. So the player is not in the radius and does not have line of sight. Here's case number 2, right? So line of sight is false, but radius is true. So the player is within radius, but again, this base enemy cannot see the player. These are inputs for the player, right? And then case number 3, line of sight is true. I can see the player, but radius is false. Okay, so this is the other one. And finally, case 4, where line of sight is true and radius is true. You can see how that circle overlaps, plus the base enemy is very close to the player and there's nothing in between. So it has both things. So those are the 2, kind of the 4 cases that we can possibly think about for the game when it comes to making assignment 3 and assignment 4. So why am I showing you this thing? Because I want you guys to think about how, when we talk about the set of information, this knowledge that is going to be given to the player, this part right here, right, is how to the AI. This is how the AI is going to respond. I have knowledge where the player is, or knowledge about the game world, which we're going to be talking about going forward in other lessons. And then I'm going to be able to do something with that knowledge as an AI. Okay. So again, there's 2 types of knowledge. There's external knowledge. So this is the information that the autonomous character knows about the game environment around it, the position of other autonomous characters, layout of the level, the player has been detected and potentially the player's position, those kind of things. And there's also internal knowledge. So this is the information about the autonomous character's internal state or thought processes. For example, the autonomous character, the AI, the agent, if you will have health, other stats, as an example, that it's going to have. Think about it as a non-player character, something that it cares about itself. Okay, there is some kind of concern, all right? It has access to ability, buffs, and special attacks, and it also has goals of its own. There's a reason for why the AI is there, okay? So those are external knowledge and internal knowledge. And typically this knowledge, it kind of drives decision-making, right? Some internal data is particular to the algorithms themselves. For example, a state machine needs to hold what state the autonomous character is currently in. Am I in idle state? Am I in a patrol state? Is the agent, the autonomous character or the AI, is it in attack state? Is it in a range state? Is it going behind cover? What is it doing? And a goal-oriented behavior needs to know what its current goal is. So we're not talking goal-oriented behavior yet. Like, what is the goal? We don't care about goals right now. We just care about simple decision-making at this point. But they control what kinds of internal knowledge these algorithms can be used, whether it stores goals, states, plans, or probabilities. And although they don't constrain what the knowledge represents in game terms. Okay, so that's something that's going to happen there. In terms of the behavior of an algorithm, let's think about this AI algorithm, decision-making algorithm. It can affect the game in 2 ways. The decision-making algorithm can request an action that will change the external state of the game. So in other words, some kind of change that it's going to make to the game world or to itself, okay? And it could also change the internal state. For example, such as adopting a new goal or adjusting a probability. In other words, I'm close enough so that I can hit better. As an example, I'm flanking the player, so the player doesn't have any kind of cover in any way. Or maybe I'm flanking the player and I have an advantage because me and another, enemy friend of mine, right, is kind of two teaming the player, so where the one enemy is behind the player and the first enemy is in front of the player, and maybe they get an advantage somehow from a probability perspective when they're trying to hit or fight the player. So again, this internal knowledge and external knowledge kind of goes into this decision-making algorithm, and then it generates an action request, and it affects internal changes and external changes to the world. So changes to the external state are not really visible. So you can't really tell, what the enemy is thinking, right? You can't really tell. You can see if sometimes the enemy can show that they're bleeding, or sometimes you can see a health bar that basically says that they've lost health, okay? But most decision algorithms, the internal state is where most of the work is done, because it's going to affect a lot of times what the enemy is going to do, okay? For example, some enemies want to take care of themselves. Like in our A3 and A4, we say when they get below 25%, they're going to run away. They don't want to die, right? So they don't want to be killed by the player. And that's an internal state because they have an internal health. They have a health. And when their health drops below a certain number, they're going to make a life-saving decision, right, to go and leave the game, that kind of stuff, right? So decision-making algorithms will carry out these internal changes in different ways. However, external actions will be identical for each algorithm. So external actions might be something like, okay, I'm going to patrol, I'm going to attack, I'm going to move behind cover, I'm going to move to line of sight, and a bunch of other things like that, okay? All right, so that is kind of an overview. So decision trees are one data structure that we're going to be talking about. This is the first data structure, and this is the one that Alex and I recommend for your assignment 3 and assignment 4, okay? You don't have to use decision-making with decision trees. You could use a state machine if that seems more natural to you when we talk about state machines, or a behavior tree. Although I have to tell you that mapping a behavior tree is way more difficult because of the way behavior trees work. It's a whole other structure of ways of doing things, okay? So decision trees might be probably the simplest way of doing things. The reason why they're easy is because they're simple to understand. They are the simplest decision-making technique, although, we can make them quite sophisticated if we want to. And they also have the advantage of being very modular because we can add more and more decisions as we build the tree. We'll talk about how to build the tree later on. So here's the problem. Given a set of knowledge, so here's your AI, right, about the current state of the game and a set of possible actions that can be performed, we need to request an appropriate action. So I got knowledge, I can see the player, I can detect the player somehow, and now I need to do the right thing, depending on my loadout. Am I going to if I'm a close combat enemy, am I going to try and run towards the player and attack them, or am I going to shoot them? What am I going to do depending on the knowledge that I have? And this mapping between input and output may be very complex, depending on what's happening here, okay, what kind of input I'm getting. And the same action can be used for many different sets of input, but any small change in one input value might make the difference between an action being sensible and an action being inappropriate, okay? So a good example of that would be, all right, well, I have an internal state, my AI has an internal state where their health is running low, like 30%. They're not quite at 25%, let's say. And they know that if they run into the player to do a melee attack, chances are they might be damaged, right? If they have a choice, maybe they're going to keep their distance and wait for the appropriate time to make the attack. That would be a very smart enemy, okay? But most enemies are going to be like seekers. They're going to be like, in our case for assignment 3 and 4, they're just going to kind of come right at the player, just like we saw in Herman's example that I showed you just earlier. We need a method that can easily group lots of inputs together under one action while allowing the input values that are significant to control the output. That's the problem. So here's the algorithm. A decision tree is made up of connected decision points, also called choices or nodes, okay? And the tree has a starting decision at its root. So example, it might have something like, I'm in patrol mode. That's what I'm doing. That's the starting decision. I haven't seen the player yet. For each decision starting from the root, one of a set of options is chosen. The choices lead either to a further decisions, some other decision, or to a final action. And each choice is made based on the autonomous character's knowledge. So again, based on the stuff that the character can see, external knowledge, or maybe some internal knowledge, right? Depending on how they're doing, if they have good health or not. Sometimes, if you want to be really unfair, you can also give the actual location of the player to the enemy through some kind of pathfinding algorithm. But typically, most games don't do that. All right, because if the enemy knows exactly where to find the player, maybe it's because they have access to a camera system or something else that can see the player. And that's why we can give the enemy that kind of information. But otherwise, if the player can't be detected, then the enemy doesn't know where they are. So they're not going to change their behavior based on the knowledge that they currently have. So when it comes to the algorithm, we want to use decision trees because they're simple and fast decision mechanisms. They usually refer to, the global game state rather than having a representation of what they personally know. And the algorithm continues along the tree, making choices at each decision node until the decision process has no more decisions to consider. And at each leaf of the tree, an action is attached. We'll talk about what that looks like. It kind of looks like this. So here's an example of what a decision tree might look like, right? So where you have a very simple decision tree. Okay, so here's the top of the tree. Is the enemy visible? And usually decision trees are kind of like yes and no, true and false kind of thing. All right, so at the top, if the enemy is visible, that'll be the player. Then we come here. Is the enemy within 10 meters away? Yes. Then attack. And that will be your close combat attack. No. Is an enemy on the flank? Yes. Move. Get out of there. No. Attack. All right, so you can see that the attack action can be accessed from two different nodes. All right, in this particular case. How about if the enemy is not visible? No. Is the enemy audible? Can we detect the enemy somehow? Yes. Then kind of creep along to surprise the player, okay, which is what they can do. I also want to give you an alternative to this for assignment 3. And we're going to share this with you later on, but here's your close combat enemy, how Alex and I kind of saw this when we kind of put it together the first time. Let's take a look. All right, so here is a possible tree for your assignment 3 and 4. Okay, so here's your close combat enemy. So is the player detected? True. Okay, if the player is detected, do I have line of sight? Yes. Then am I within a close enough distance? Yes. Then do a close combat attack. This is your decision tree, right? If the player is detected, no, false, well then keep patrolling. Keep patrolling, keep patrolling, keep patrolling, all right? So this is a possible decision tree to start off with. Things that are missing in this tree are things like, hey, what happens if I go lower than 25%? Let me show you one more, all right? So here's one type. Here's the next one. What about the range combat enemy? And let's update the tree a little bit and make it more complex. We can call these alarm decisions, okay? Here's an example. Instead of staying if the player is detected, like right here, here's the player detected part that we just showed you. This is kind of a subtree, okay? By the way, trees are made up of nodes. Here's the root node. And then these ones, so that's when we look at the tree algorithm itself, this one, this one, this one, this one, this one, this one, and this one. Notice that these ones here at the bottom, these are leaf nodes, and the leaf nodes is where the actions occur. So this is where the actions happen, right here, right? Patrol, move to line of sight, move to range, attack, move to cover, wait behind cover, right? And then you have something called alarm conditions, okay, where, okay, my health is less than 25%, okay, get out of there, flee. My health is not less than 25%, then has the enemy been hit? Remember, because the enemy also has an alarm condition. When they get hit, they're going to move behind cover. This subtree, which is right here, sub-decision tree, is where they can move behind cover. Again, this is one possible example of a decision tree we can use for assignment 3 and 4, okay? Or mostly for assignment 4, actually, okay? And this part here, this is another subtree. So for this part right here, this is another subtree. And this subtree right here, this part, is based on if the player is detected or not. So again, going back to what we showed earlier, if the player is detected, that's an alarm. Well then, do we have line of sight? Yes. We are within range? Yes. Attack. Otherwise, move to range. Right. So this kind of thing is kind of a repeat from what we saw earlier. All right. Questions around decision trees, the structure of decision trees, when you look at this from the first time. For some of you, this might be a little bit foreign when you're looking at this like, wow, it's really complex. But think about a series of if-then statements, right? If this, then that. If this, then that. If this, then that. If this, then that. At the basic level, that's really what a decision tree is. A bunch of true-false statements as you go through to select the appropriate action to take based on the knowledge or the information that the enemy AI has. Okay, that's what it is. All right, so we'll come back to this again, and I'll share these two diagrams with you later on. Maybe we'll even make another one that's more specific to what we're doing. So this is an example of what the algorithm might look like, okay? So again, you can see that this is the path that it would take. So like I said before, either yes, no, or true, false. There's a direct path to a particular action, the single action that's going to be taking effect at the end, okay? So again, decisions in a tree are simple. They typically check a single value and do not contain any Boolean logic. And depending on the implementation of the data types of the values stored in the autonomous character's knowledge, different kinds of tests may be possible. For example, a Boolean test, the value is true or false. Some kind of enumeration, right? Or a numeric value, or some kind of 3D vector. It's really up to you, or 2D vector. It's really up to you how you detect or use this information. For most of the time, the things that we're going to do, think about this data. Enemy is visible. I have a Boolean, true or false. I can see them. The enemy is within 10 meters away. That's a value. So again, if you think about what that means, that's like, okay, I need to know what the distance is. So I can test the distance value, okay, and so on. All right, so we can combine a lot of these decisions together. So decision tree is efficient because decisions are typically very simple, and those that are less performant are also only called when necessary. Less performant decisions, as an example, are things like if I have to heal or something else like that, or I have to leave and come back, or those are less performant because, again, they're not as effective as firing or fighting with the player, okay? Very quick decision making. Each decision makes only one test at the end of the day because each decision level, if you think about what we talked about before, right, when we talk about this is the first decision level. Is the enemy visible or not? This is the second decision level. This is the third decision level. Each one of these three things, these little diamonds, represents a decision, right? What am I going to do next? One decision may lead to another decision, and so on. And finally, to a final action. So trees representing combinations of and or. So again, if A and B, then do action 1. Otherwise, do action 2. So if A and B are true, then do action 1. Or if A is not true, then do action 2. If B is not true, then do action 2. You can see that action 2 is repeated twice. The other way to do an or decision is if A or B, then take action 1. Otherwise, do action 2. Different way of doing things. So again, I have action A or decision A. If it's true, then do action 1. If B is true, then do action 1. Otherwise, do action 2. So this is other ways of combining and representing decisions for a particular tree. When it comes to complexity, you can see that in this particular case, there are different levels for the decision tree. So this is the first level, and you can see that how many levels deep is this? 1, 2, 3, and then finally you can see all these little squares here are all action states. So the action states are always at the bottom of the tree. This is just a tree that's on its side, right? And we can also think about this. If I was to rotate this tree a little bit, let's just do that. Again, you have these PowerPoints, they're up online for you. Well, let's suppose I rotate this tree for a second, and if I look at something like this, what we also talked about is, from a data structure perspective, is the idea of a subtree. Okay, so sure, this is a tree. Each tree has a couple of parts. One of them is the node. This is a decision node. A connection. This is the connection, right? And some kind of decision at the end. This is the decision, okay? And we also can say that if I look at this part right here, this is the left subtree, okay, for this particular tree, and this is the right subtree. You can see that this is a very symmetrical tree, and usually when we see a tree like this is a binary tree, okay? Binary tree means that there are at least 2 decisions for every node, okay? And this would be awesome if you had something like this, because then it's very easy to kind of eliminate one side or the other side, okay? But inside of this left subtree, there's also other subtrees. If in this left subtree, then this is the root node of this left subtree. This is the root node of the entire tree, okay? But this is the root node of the left subtree. And you can see that in this case, you have another left subtree that's in here, okay? This is another subtree, right? And if we think about this, if I keep on looking at subtrees, a tree within a tree within a tree, right? As an example, once I start going in this pattern, what would be the right way to traverse the tree? If you think about this, if there's a tree within a tree within a tree, what, in your case, what do you think would be a way of traversal or creating this tree? What's one way of doing it? What's one method we could use, if you will? Anybody? Tree within a tree within a tree. Almost like Russian dolls. A doll within a doll within another doll. Okay? Anybody? I'm going to call upon you guys again. I can see you guys here, right? You're not safe. Just because you're watching doesn't mean I can't ask you questions, right? So talk to me, guys. What do you think would be what does this thing how can we represent this thing in a different way? Or how would I traverse this tree? Anybody? It's very quiet this afternoon. Derek says, find the left and right node as a tree, as the next tree root continue to the leaf. Yes, you could. But how do you do that? Would you use a while loop? Would you use a for loop? What other kind of looping structure? Fabian's saying an if else. Yeah, you could. That's if else would be in the actual tree itself. But what I'm thinking about is something like recursion. Think about this. If I have a recursive algorithm, right? An algorithm, a function that calls itself. And because this is so well structured, it's exactly the same way, then instead of using a while loop, right, we can recurse from one subtree down to the other one. And then we can return the decision. We can bubble the decision up to the next layer, the next layer, the next layer, until this layer here is going to have the decision that's finally been chosen at the bottom. Okay, so this is the decision that's chosen. It's going to bubble up all the way to the top layer, and we can use the recursion for this. Recursion is dangerous, and recursion also is not really recommended for most beginners, because when they start looking at this, they're like, wait, what? Recursion? That's dangerous because we could have a Stack Overflow or something weird like that. And if you've learned about recursion in your C++ programming class, you know that there's always a way of doing the same thing with a while loop as you can by using recursion. But recursion is kind of like a simple, sleek little algorithm you can make. One thing to get right when it comes to using recursion is something called the base case. The base case is always, challenging to figure out. Yeah, Stack Overflow, exactly. All right, so I'm showing you this because I want you guys to think about, how do I implement this thing? How do I implement the tree structure in the first place? All right, so let's move on. So again, decision tree, there's 15 different decisions and 16 possible actions. That's what this is. After the algorithm is run, we see that only 4 decisions are ever considered. See, this is the black line here. 1, 2, 3, 4 decisions. And that's why this is a very sleek little tree. We can build this tree with all these different actions and all these different decisions. But again, only one action will be selected based on the external or internal knowledge of your AI. So again, they're relatively simple to build when it comes to making decision tree. We can build them in stages, and a simple tree can be implemented initially, and then we can add more complexity to it, which we're going to do in our labs. And we can add more decisions and add more behaviors or more actions. When it comes to branching is something that we're talking about here. Branching is a kind of a little bit of terminology that we're going to use. Typically, branching is if else. If this, then do that. Okay, that's branching. Branching is very, very common. We've seen it in programming fundamentals, C++, when you're learning C++. Branching is bad when it comes to graphics. You don't want to ever branch when it comes to doing something every frame. Okay, branching every frame makes your CPU slow down. Right? I just wanted to put this out there. But branching is pretty much what we're going to be doing. So imagine you have a guard, which is an AI, right? In a military facility. The guard needs to make decisions based on the current alert status of the base, right? So there's 4 different statuses. Think about this as an enumeration or an enum, right? Green, yellow, red, and black. So this is the example that we're looking at here. Using the simple binary decision tree described above, right? We talked about this. We'd have to build the following tree. Are we in black state? No. Is it red state? No. Is it yellow state? No. Well, then take the green action, right? Is it in black state? Yes, then take the black action. Is it a red state? Then take the red action, and so on. And this is kind of something called a deep binary decision tree. Okay. So again, the same value or alert state may be checked 3 times. Because why? Because we're checking to see if all of these states are checked over and over again. And this is okay, but maybe there's a more efficient way of coding your tree. Here's another way of doing it. Okay, which alert state are we in? Black, red, yellow, or green? Okay, depending on which alert state you're in, then choose the action. So now you're only taking one action, right? So this is more of a flat decision tree with 4 branches, okay? Another way of doing things. This doesn't have to be the way we showed you with a binary decision tree. This structure is flatter and only ever requires one decision and is obviously more efficient, okay? However, it's more complex as well. Despite the obvious advantages, though, it is more common to see decision trees using only a binary decision, so true-false, like we talked about before. The underlying code for multiple branches usually simplifies down to a series of binary tests, true-false, right, or yes-no. Although the decision tree is simpler with multiple branches, the same underlying code is being run, and its speed is usually not significantly different. Why? Because at the end of the day, your CPU is running through those decisions very, very quickly every frame. Most of the common learning algorithms that work with decision trees require them to be binary. That's another reason why you want to use binary trees, right? So if we're going to do any kind of machine learning or reinforcement learning in the future and improve your algorithm, make it a binary tree as much as possible. So here's some pseudocode when it comes to making a binary tree. A decision tree takes as input a tree definition, okay? So some kind of tree class consisting of linked decision tree nodes, like we talked about before. Decision tree nodes might be either decisions or actions. Those are the 2 types of nodes they can be, all right? In an object-oriented language like C++, these may be subclasses of a base tree node class or implementations of a common interface. It's really up to you. In each case, a method is specified that is used to perform the decision tree algorithm, and it is not defined in the base class. Example, here's my decision tree node, right? And notice it says recursively walks through the tree. So function make decision, which returns the next decision tree node. Okay, that's what it does. This little arrow means returns. So actions simply contain details of the action to run if the tree arrives there. So again, remember, we talked about earlier, if I go and I navigate through the tree itself with different decisions, I come to an action at the end, right? So that's the action that's going to be taken after I've navigated to that point. Okay. That's what actions are. So their structure depends on the action information needed by the game, and their make decision function simply returns this action. So for example, make decision returns the decision tree node, and usually what it does is it returns this. That's the action that you're going to return. Again, notice that it extends a decision tree node. So a decision tree node is something we're going to have to create in our labs as we go forward. Something like it anyway. So decisions have the following format. A decision extends the decision tree node. There is a true node and a false node. Typically what we do is just like I showed you earlier, I like to place the true nodes. Let's look at the ranged combat enemy for a second. I like to place the true nodes on the right side of the graph, right? Because this is what this is. If you look at this, this is a graph. So the true nodes go on the right and the false nodes go on the left. This is just my convention. But it's totally something that you can do. As an example, Derek's giving us some examples here. But yeah, that's pretty cool. So the true node always goes on the right. The false node goes on the left. And then you have a consistency when it comes to building your tree. Okay? And yeah, Derek has some examples. So node is a true node and a false node. There you go. And you're using a get action to return a node. Very good. I like it. And we'll talk about more about this in lab. So yes, something like this is good, Derek. Okay, so very good. So let's go back to this. So again, so far we've been talking about the structure of making a decision. Again, one thing is there's the test value of some kind. And a lot of times, again, this is more complex, but we have a get branch, which is a perform the test, or recursively walk through the tree by make the next decision if there's a decision to be made. Okay. A lot of times, there are different forms of the decision tree node structure for different types of tests. For example, a float decision, which extends the regular decision. So instead of having a true or false, we have a min value and a max value. And what we want to do is our test returns that value. That's the test value that's returned. And if the test value falls between the minimum and maximum, then it meets it. We return the true node. Otherwise, we return the false node. Example would be, am I in range? Right? So if I have a minimum range and a maximum range, minimum range is 10 pixels, maximum range is 100 pixels. If I'm between 10 and 100 pixels, fire your weapon, as an example. Otherwise, don't fire your weapon, right? That's kind of an example of how that would work. Again, a decision tree can be referred to by its root node, and the first decision it makes is the top of the root node. Okay, so that's patrol action as an example. Or if I go back to what we saw in the diagram, is my health greater than 25%? Okay, that's the root node. If it is, then check the next thing. Has the enemy been hit? Have I been hit? Then have I detected the player? If I haven't detected the player, no, well then patrol. And this is the default action. So the default action that it starts off in is probably going to be something like patrol. That is going to be the first action that the enemy might take, as an example. Okay. We can implement a decision tree a decision that supports multiple branches almost as simply. But again, what we want to do is we want to only have a couple of daughter nodes or child nodes, if you will. And the reason for this is because we want to kind of meet the binary tree criteria just in case we want to apply some kind of learning algorithm in the future. Okay. One thing that we also want to talk about really briefly is knowledge representation. So decision trees work directly with primitive data types. Okay. So example, integers, floats, booleans, or something, right? And a lot of times these states are kept track of. For example, what's my health, right? That's a floating point value, float, right? Or an integer maybe. What's the distance between me and the player, the enemy AI and the player, right? That is it might be a floating point value in terms of, or an integer value in terms of the numbers of pixels that are between me and the player, right? Is the player hurt? Can I detect if the player's been hurt? Do I see them bleeding or something like that, right? Well, that's a true or false value. They're either hurt or they're not hurt. I can detect them or I can't detect. Do I have line of sight or do I not have line of sight? Are they within my detection radius or not, right? So this is kind of knowledge representation. So again, decision trees typically have, they use the knowledge of the game directly. So external knowledge somehow. So, again, sometimes the structure of, during development, when we're working together and coding this stuff, the structure of the game state often changes. Like something like a decision might detect, for example, which direction a security camera is pointing, but if the underlying implementation changes from a simple Euler angle to a full quaternion, well, that could, kind of maybe make the decision break. So this is something you have to keep track of when you're coding. And this is part of the discussion when it comes to how we're developing the AI system. Okay. When it comes to performance of decision trees, they're pretty darn good. And the reason for that is they're pretty much linear, right? Which is the number of nodes visited is how long it takes for the tree to perform. And again, remember, it's true, false, true, false, true, false, true, false. And then, okay, I have an action to perform that action. So you're going to see that the decisions change very, very rapidly, okay? Now, this is good, right? But it also can be really bad. And I mean that in terms of jitter. So here's an example. Let's go back to that diagram, right? So has the player been detected? True. Do I have line of sight? True. Am I in range? True. Attack. Okay? I attack. Am I in range? Attack. I'm always going to loop back every frame to the top of the tree. Do I have health? Have I been hit? Has the player been detected? Right? Well, the player detected, this is kind of something that's going to always stay on. The player's been detected or not, right? And notice that there is has line of sight is on the right-hand side and has line of sight is on the left-hand side. So again, if I have line of sight and I've been hit is different than if the player is detected and I have line of sight. Having line of sight has two particular different actions depending on my alarm state. Am I hit or not, right? If I'm hit, then line of sight means, hey, the player can see me. If I can see them, they can see me, right? And so on, right? So that's something that you want to think about. So again, it's very linear. So you can see that there's a finite state of a set of decisions to make before we get to the action. And even in a more complex tree structure like this, again, the decisions are made very, very quickly. But imagine if I'm shifting back to, well, I'm not in range. Okay, I move to range, then I attack. I move to range, then I attack. And if I do this over and over again, sometimes it'll cause jitter. And a lot of times what we want to do is implement some kind of holding pattern or a latency for making those actions. You don't want to switch between actions super fast every frame. You want to wait X number of frames in order for you to make an action. And that delay makes it so that the AI is more believable and less jittery. When it comes to balancing the tree, here's the example of a binary tree, right? But that's very unbalanced. It's the exact same number of decision nodes. Here's the decision nodes, right? As this one, and the same number of action nodes as this one, but it's laid out in this way. Think about how many decisions I'm going to have to make to hit H or G, right? 1, 2, 3, 4, 5, 6, 7. Worst case scenario. Here, if I want to hit G or H, any one of these bottom nodes, worst case it'll be 2, right? So the first decision plus 2 more, right? So 3 total. Let's say worst case scenario. Here, worst case scenario could have many, many more decisions. So this is an unbalanced tree, and this is a balanced tree. Both are binary trees because they have left or right trees, right? Structure. But a balanced tree is what you want more often. And a balanced tree makes sense because it's optimal compared to what if a tree looked like this. Okay. So balancing the tree is important because, again, it cuts down the number of decisions that need to be made. Again, although balancing the tree is theoretically optimal, in practice, the fastest tree structure is slightly more complex, right? So in reality, the different results of a decision are not equally likely, right? If we were likely to end up in behavior A, as an example, the majority of the time, then the first tree would be more efficient if it gets A in one step. So example, let's suppose that A is the most common action, right? If I can get to A in one step, it's more efficient than this balanced tree because this balanced tree would take 1, 2, 3 decisions to get to A. Actually, minimum number of decisions for any one of these results is 3. Here, it could be 1 or 2, right, to go to A or B. So although this looks awful, right, you know, sometimes it can be more efficient or way less efficient depending on what's more common, what's more probable. And sometimes people code it like this because the more probable decisions happen here, things that are most common, okay? Okay. So in addition, not all decisions are equal. A decision that is very time consuming to run, such as one that searches for the distance to the nearest enemy, should be only taken if absolutely necessary, because searching for the distance, you're going to have to do some kind of calculation like square root potentially, or square distance. And that square distance check is going to be far, far longer than do I see the player or not. Okay, that's more of a collision check. So let's keep moving, kind of beyond the tree. In strict branching, right, as an example, we've been kind of keeping strict branches, but notice that some of them, sometimes what we can do is we can merge branches together, right? So notice there's a decision here and a decision here and a decision here, but these two decisions merge into one other decision. If you do this one or this one, you still go to this part. And we just saw this as something that looks like this. If I was going to rebalance this tree, notice that there has line of sight is happening twice. Maybe there's a way of kind of combining these two checks, has line of sight. Depending on if my enemy is hit or not, if that alarm condition is there, it might be another check that I can kind of branch over to this part. Is there a way, is what I'm asking, to simplify this kind of tree, to make it even easier to code, right? Because again, you can see that we have two different branches here. This is one possible representation. Maybe there's others that you can think about. Another way of setting this up. Try it for yourself. Make a bunch of boxes. This is kind of like an exercise for you, right? And with these boxes, try and think about, all right, if I was going to look at assignment 3 or assignment 4, let's say, and I was going to try and map out all the possible actions to decisions, how would I do it, right? Can I simplify Tom's tree or Alex's tree, what they're showing us right here? You know, and quite often we've seen people come up with, some other representations of this of a tree structure that's different than ours. Okay, so you can merge branches. The other thing is that there's also something called a pathological tree. Pathological tree is where you have a branch that goes back to the previous branch, okay, as an example. So this pathological tree structure that we're seeing right here is typically not something that we want, okay? Because if I'm going to go back, I can have, the reason why it's called pathological is because it continues to loop over and over and over and over, nonstop, right? And this looping structure that's happening right here can lead to an endless loop if you're not careful, right? Or maybe that's what you want. Keep patrolling, keep patrolling, keep patrolling. And that might be the action that you're getting unless you, for example, you have line of sight. This is another way of representing the same thing. Sometimes what we also want to do to keep it fresh is make random decisions, okay? Imagine if I have the exact same decision that an AI is going to make every single time, okay? Example, if I hit the AI, I just said to you guys, if the ranged combat enemy in assignment 4 gets hit, the first thing they're going to do is kind of run behind cover. If I know as a player that that's what they're going to do every single time, I can predict what they're going to do and kill them, go find the place where they're going to find, run behind cover right away. If I can calculate where that's going to be, kind of the closest place to cover, which is what we said. If I can recognize that as a player, I can predict the AI. When the AI becomes predictable, it kicks me out of my sense of, disbelief. It kind of, kicks me out of immersion, if you will. And I suddenly figure out a way of beating the AI in the game, which is always, once you start beating the AI in the game, you can figure it out what they're going to do because it's a very, very simple AI. It becomes almost like underwhelming in terms of the challenge that you're going to get, right? You don't want a predictable AI. So one thing you can do is you could generate a random number to choose a branch based on its value. So let's suppose I've detected the player. Maybe there's a 30% chance, even if I've detected the player, I'm going to keep patrolling until I can see the player, right? And maybe there's a 70% chance that if I've detected the player by hearing them, I'm going to try and find the closest node to line of sight. Maybe there's another chance that maybe I'm going to alert someone else, right? I'm going to alert another AI because now once I detected the player, maybe there's some kind of chance if I'm some kind of guard that I'm going to pull the alarm, right? There's some kind of chance that I'm going to do that. And that random chance stuff makes the game that much more interesting. So again, imagine running the following tree every frame, right? Am I under attack? Yes, then defend. No, then flip a coin, as an example. If I get heads, I patrol. If I get tails, I stand still, right? So that makes it so that it is, it's a little bit more random. And so we don't want it to flip between these two states every single time. Otherwise, what's going to end up happening, my friends, is if it continues to vacillate or flip between these two states, it's going to produce that jitter. You want to be able to stand still or continue doing making the same decision or taking the same action you took last frame until your external knowledge has changed. I can see the player. I can detect the player. I get damaged somehow by the player. As an example, external or internal knowledge, and then you can make another decision. So keep doing the same thing. Otherwise, it's going to really be a lot of jitter. So to introduce random choices in the decision tree, the decision-making process needs to become stable. Okay, so again, if there's no relevant change in the world state, there should be no change in decision. This is really important. And the reason for this is because it's not going to look right. It's going to look very unnatural for me to switch decisions based on new information every frame. Maybe you want to wait 30 frames, like a whole second before you make a decision, or half a second, something like that before you make that a decision based on a change of external state. So again, one other thing we don't want to do, which is mentioned over here, is you don't want to always do the same random thing. So if you want a variety of choices to be shown, keep track of the last decision that you made. So if you decided, as an example, this time to patrol when you detected the player or pull the alarm, maybe the next time you're going to try and move to line of sight. So you don't always try and do the same things. Okay. And that's for the autonomous character. And here's an example of some pseudocode for a random decision that extends the regular decision. So again, the current decision is false if the test value, if, for example, whatever the current frame is, if the frame is greater than the last frame plus 1, and what we're doing is we're kind of making a random decision based on, how many frames have passed. If the agent continues to do the same thing forever, it also looks weird. So for example, if I'm always making the patrol action, I'm always making the fight action, I'm always making the flee action, it can also look really weird. Again, in our example, it could leave the agent standing still forever, which kind of looks really weird, right? Standing still or patrol. And if you're standing still for a long period of time, you want to be able to time out an action so that way you can, kind of reset, if you will, the decisions that the enemy can possibly make. And so there's a random decision with timeout pseudocode is what it looks like here. And I've included it here for your notes, but I'm not going to talk about this right now. All right, so we've gone through most of what I've talked about when it comes to decision trees. Any questions? Are you good with it? How do you feel about decision trees in general? We haven't actually coded them because we're going to do that in lab. But how about the idea, if you will, the high-level idea about decision trees? How are you feeling about that? Are you more comfortable with it now that we've talked about it, or do you still feel very uncomfortable? What are your thoughts, guys? Like we said, this is the simplest level. And the reason why we're saying it's the simplest level is because it is adaptable. It is something we can build on. We can modify the decision tree if things change. We can build this very simple decision tree and modify from there. What are your thoughts, guys? You guys are very, very, quiet this afternoon. Okay, Vander says more comfortable now. Good. And we're going to get more and more comfortable as we go, because at the end of the day, you understand the basics. I think we've talked about it in lecture. But what we want to do more than anything else is we want to practice it, actually create the tree during our lab. So our lab sessions are super important. And it's important because we actually implement the stuff that we're talking about here in lecture. Okay, so please make sure you come out to labs every single week. Okay. So what do we do for lab 6.1 for this week? What we did was we talked about this line of sight system that we wanted to develop. Okay, and again, the line of sight system that we talked about in lab 6.1, I called it lab 6.1, it's like lab 6 part 1, if you will, is fundamental for both A3 and A4. Without line of sight, as an example, then really we don't have one part of our external knowledge that we need for assignment 3 and assignment 4, right? So what I've asked you to do for assignment for lab 6 is download that new starter. We had to make some changes to it. We included a starship, a target, and obstacles. We created a new path node class. We created a grid of path nodes. We used IMGUI to hide the path nodes, that blue square. And we added primitive raycasting to the starship that detects if it has line of sight with the target. That's what we kind of did this week in our class. One thing I haven't done is uploaded the recording for our lab, which I will do most likely by the end of the day or tomorrow. Okay, so again, it's meant to be in person, but for some people that are not able to make it in class, I will always record the lab worst case scenario so that you're able to do it whether you're in person or not. A couple things to note in terms of administration now that the lecture part has been done is takeaways from today's session. All right, so one thing we talked about is that we're doing labs. And one thing that Philip is doing with you in game production too, like we mentioned, is that he is going in class, so doing in-person learning, as well as remote learning, teaching and learning, depending on the schedule. So the outline tells you which weeks you're supposed to be in person and which weeks you're supposed to be remote. And he sent you guys a note saying, as an example, that next week we're going to be remote. So next week, please don't come to class for the lab. We're going to do the lab remotely as well because I don't want any of you to come to class for 2 hours, okay? That's not what we want. So please make sure you attend remotely, okay? And we'll use the same link, the same Zoom link for the remainder of semester. So you don't have to hunt for a new link. I've also put the link for you guys from an administrative perspective on the left-hand side here on Blackboard. So you can see that there's a Zoom link for second half of semester. you click on there and it'll teleport you to our call. Okay, this is the thing that we want to do. Also, just like we mentioned in the content, if you notice, I've hidden away all the lectures from the first half in a module, right? You can always go to week 9 for this week, and you can see that there is a recording for the lecture. This is the lecture recording that we're doing right now, which is also live on YouTube. Okay, so you can watch the lecture in 2 different ways. You can watch it after the fact, or you can participate in the live YouTube broadcast right now. And for example, some people would want to do that if you're not a native speaker. YouTube provides you a lot of times with real-time closed captioning support. So if you want to do that, you can use the YouTube link as well. This is kind of cool. And it'll be the same link when you watch the recorded lecture. So I'm kind of doing 3 things at once. I'm on Zoom, I'm on YouTube, and I'm recording the lecture all at the same time. And that's what we're going to be doing for next week for both lab and lecture. So Tuesday's labs, again, the first lab happens at 1 o'clock from, for example, from 1 to 3, if I'm not wrong. And that is where we're going to record the lab. All right. So again, you can all attend one lab section, and I will use the last part, hours 3 to 5 for any kind of questions you might have. We can kind of get together for any Q&A for your assignment or whatever. We can use that portion for that. For that lab portion from 3 to 5 p.m. next week. If you have any questions you want to ask for your assignment 3 coming up. Okay, or even for your lab 6, which is going to be due not this week, but next week. Are we clear? So next week, please do not show up to class in person. It's going to be fully remote because Philip is remote. Okay. Let me come back to your question, Derek, in a second. Any other questions related to or concerns around the timing or the production of your lecture and lab videos? Okay. Derek has a question. Derek says, I have a question of line of sight. If the target is small, that is in the range of line of sight, but it cannot collide by lines, so the solution is generate a lot of lines, thank you, that are more dense or using it some other way. Yeah, so what Derek is referring to is this idea of what happens if, I'm just using one simple ray to detect, kind of the enemy or the player. So let's try it out. So imagine if, right, we have this is our target, all right, here's our target, and we have a, kind of the enemy AI that's right here. And if I only cast one ray, so if I have a ray, let's make that ray red. Okay, as an example, here's that ray, red ray. And if I use a line, so I cast a line that's straight, that goes here like this, yes, you can clearly see that if this is the target, let's just name this as the target, right, as an example. And since we're doing our drawing here, here's the target. You can clearly see that we're out of range right now, right? So this is some outside of range. This is one scenario. But what Derek is talking about is, let me just do this. What Derek is talking about is what if, right, as an example, what if I'm like this? I'm here. I mean, I'm clearly in range, but somehow I don't have line of sight, right? So this may be a little bit unrealistic, right? In a real world scenario where line of sight is not just a single ray, but is made up of many rays, just like you did for your obstacle avoidance. Like, for example, creating a whisker, right? Or instead of using ray casting like this, maybe you use some kind of box collider. For example, maybe instead of using a ray, you use a box that looks like this, right? So this kind of thing, right? And this box, as an example, is the thing that you're using, right? So here's the box, and we can see that now, even if you're not exactly aligned with it, well, you've got line of sight. This is a way of doing it too. And some people also do a much more complex shape where they want to collide, some kind of other type of collider, where they have like what it looks like just like line of sight. So example, like we had before in your obstacle avoidance, some kind of line of sight that looks like this, right? Where you have more than one ray that you're casting, and then you create a shape, almost like a mesh, right, that you kind of create. So anything that kind of collides with these two shapes, right? This is something you can do too. It's more complex, Derek, but it's possible for sure, right? If I do one of these, I can see the player, especially if I'm rotating, like, you know, I'm doing one of these, you can see that that works okay, as long as it's in that arc. This is kind of an arc, a way of seeing the player. It's also possible, but more complex. For your assignment, we're simplifying. We're saying if you don't have line of sight, you know, as an example, then that's where we're giving the AI sensing suite two parts, which is either line of sight, let me just undo those changes, line of sight, or some kind of detection radius that starts at the in the center of the you know, of the enemy. So one of these two things. So even if I don't have line of sight, I can't exactly see the player, you know, as an example, but you know, the AI sensing suite would also include something that looks like this. So for example, if I'm moving around, I don't see the player, but hey, I detect the player, then what I can do is I can kind of pivot to see the player because I detect the player where they are. So that's kind of another way of doing the same kind of thing. Okay, where we're using some kind of radius. Does that answer your question? Yeah. Okay. So again, so that's just to go back to the administration piece. Anybody have any questions relative to the assignment? No problem. Thank you, Derek. For any questions around the assignment, any other questions relative to the, you know, to anything that we've talked about before so far? All right. If you don't, if you're all good, check mark. Let's see if you can do the check mark on Zoom. Check mark is a reaction. So if you look on Zoom, you can do a check mark. Let's see if you guys can do that because we're going to talk about that next week when it comes to, no, that's, so Zamarco, that's pretty cool, but see if you can do the check mark on your reactions. I see some people doing that. There we go. It's not in the chat, but actually on the, as a reaction. I can see that you did that, and Jaden, you did that. Marco, you did that. Okay, there we go, Zamarco, I got you, right? Abu, you're good to go. Fabian's good to go, all right? How about the rest of you guys? So I'm going to ask you that a lot. One thing I do a lot is say something like, are you with me? Thank you, Vander. And when I say, are you with me, I'm expecting check marks. And the reason for this is because, thank you for that feedback. The reason for this is because there's many more of you than of me. And for me to look at a chat is more difficult, thank you, Marco, than, you know, than kind of looking at a bit of a check mark. Okay, so please let's do that next time. When I say, are you with me? Check mark. Okay, and then I know you're alive. And I don't have to keep, you know, kind of waiting for your responses. Okay, guys, that's really it for today. I covered decision making, a little bit of an overview. I talked about 3 methods for making decisions. We talked about decision trees, state machines, and behavior trees at a very high level. We focused this week on decision trees. Next week, if you look at the schedule, we're going to hit state machines. That's what's coming up next week. And we're going to finish off Lab 6 when we get together during our Tuesday meeting. Okay? That's it for me. Again, look for the Lab 6 Part 1 recording that I'll put up later today or tomorrow. Otherwise, that's it, guys. Thank you so much. I'll stop recording now, and I'll take any questions you might have. Okay, the recording has finished. Any other questions before we go?